Hello everyone, we are starting Chapter 7. Can you believe we're already halfway through our AP Statistics course? Chapter 7 is a doozy of a chapter. We're diving in to some more inference types of statistics as opposed to just descriptive statistics. This chapter, or specifically this section, is going to be all about a sampling distribution. What is a sampling distribution? By the end of this section, you should be able to tell the difference between a parameter and a statistic. And these are terms that you've heard before. We talked about them at the very beginning of the year, but we're going to dive deeper and make sure we really get them now. We're going to be able to define the term sampling distribution, be able to distinguish between three different distributions: a population distribution, a sampling distribution, and also the distribution of sample data. We're going to be able to determine whether or not a statistic is an unbiased estimator of a population parameter, and then also describe the relationship between sample size and the variability of an estimator. The process of statistical inference involves using information from a sample to draw conclusions about a wider population. Different random samples yield different statistics, obviously. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. All right, let's unpack that a little bit. So we need to be able to describe the sampling distribution of possible statistic values. Statistic values could be things like sample means, or sample medians, or sample proportions, right? These are all statistics of a sample. And those statistics can be seen as random variables. So we can do things with those data like we did back in the previous chapter with random variables. So we have some population, we take a sample from within it, we collect some data from the sample, and then use that to make an inference about the population from which we gathered the data. Another kind of little visual to help you out. We want to know about these. Here's our population. So through random selection, whether that be a random sample or random assignment and an experiment, we take some data. We gather a statistic from it. So for example, you gather a sample mean. Use that to make an inference about the population mean that we don't know. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. Very crucial here, folks. A population has a parameter. The parameter is a number that describes some characteristic of the population, like the population mean, the population proportion, the population standard deviation. Typically, we don't know this, and we generally use Greek letters to describe it. So think mu, sigma. Now, the sample has a statistic. A statistic is a number that describes some characteristic of the sample. This can be computed directly or used and also used to estimate the unknown parameter. We're going to do either we did or we're going to do an example of this in class together. Symbols are very, very important in statistics. So you want to make sure you know which symbols mean what. As far as statistics, and like not statistics class, but statistic, the number that describes a sample. P hat describes proportions. X bar describes means, and lowercase s describes standard deviation. For the parameter, for the population, regular old P, and it's a lowercase p for proportions, mu for mean, sigma for standard deviation. Please, please, please know these symbols. If you're going to use them, you need to make sure you use them correctly. Okay, let's go through two examples together. We want to identify the population, the parameter of interest, the sample, and also the statistic in each of the following examples. For A pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys So she takes a sample of 50 patients and calculates that the third quartile is 56 inches. What is the population? All 10-year-old boys. That's what they want to know. She wants to know about. The parameter, what do we want to know about those 10-year-old boys? We want to know the 75th percentile, or if you want to say the third quartile is fine. Was she able to gather data from all 10-year-old boys? No. So we took a sample of 50 10-year-old boys that were included in the sample. And from those 50, we gathered the data and found out that the statistic, the third quartile, the 75th percentile, is in fact 56 inches. Next example, a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. Population, who do we really want to know about? All 12 to 17-year-olds. And you remember, the population describes the bigger picture from which the sample was drawn. So since our sample, it's actually easier to describe. We sampled 1,102 12 to 17-year-olds with cell phones. Actually, that would not be quite correct. That's better. We didn't specifically seek out people with cell phones. We just sought out 12 to 17-year-olds. And so, yeah, that's better. So the parameter is what proportion have cell phones, and our actual statistic, the p-hat, the proportion of these people that do have cell phones, is 0.71. All right, sampling variability. The value of a statistic varies in repeated random sampling. This is normal. This is a dot plot that we can see is an example of when we did the card example. So when we selected a sample of 5 cards and got the median is not going to be the same every time. This is from a previous year's data. When repeated many times, though, we can evaluate the SOCs of the distribution. So remember the shape, the outlier, the center, and the spread. Remember the general definition of a distribution. We talk so much about this word distribution, we sometimes forget what it actually means. A distribution is just going to be a list of all of the possible values a variable can take and also how often it takes those values. So this is a distribution. Okay? Now, the sampling distribution of a statistic is a distribution of values taken by the statistic in all possible samples of the same size from the same population. It has to have all those things. So it's all possible samples as long as they're from the same size and from the same population. Now, this dot plot here, is it truly a sampling distribution? No. All right, the dot plot that we made representing the sample medians is not, because we did not include all possible samples of size 5. There would be many, 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 many more. So this is just an approximation of a sampling distribution, which is typically what we're going to see. It's going to be too hard to truly get all samples of the same size, so we're typically just going to see approximate sampling distributions. So like I just said, in practice, it's difficult, usually impossible, to take all possible samples of size n to obtain the actual sampling distribution of a statistic. But what we can do is we can use simulation, typically through technology, to imitate the process of taking many, many samples. One of the uses of probability theory in statistics is to obtain sampling distributions without simulation, and we're going to get a little bit into that theory later. Let's go through an example. This is the simulation of 500 simple random samples of size 5 from the modified deck of cards that we used earlier. So we're still going with that card example. The graph to the right shows the distribution of the sample median for these 500 samples. Now, in this case, we're doing median. We could have done mean, we could have done some other thing, right? We could have done Q3, we could have done range, whatever, but we chose to do median. A couple questions. Is this a sampling distribution? Describe the distribution, and then talk about some convincing evidence. So first off, no, this is not a sampling distribution. The distribution didn't use all possible samples of size 5, So this isn't an exact sampling distribution. It's only 500 samples. There would be a lot more than 500. Let's describe it. So go through your socks. Shape. It is roughly symmetric with a single peak at 6. Okay. Center. The mean of distribution is about 6. Spread. In lieu of actually calculating something, which we'll learn in a later section, for now we can say that values fall mostly between 4 and 8, although there are values as low as 2 and as high as 10, and there appear to be no outliers. C. Suppose that another student got a median of 4. Is this convincing evidence that a student's deck of cards was modified incorrectly? Getting a sample median of 4 does not provide convincing evidence that the student's deck was modified. Getting a sample median of 4 or lower occurs fairly often just by chance when taking random samples of size 5 from a deck of cards with the aces and faces removed. This was a common thing I saw in the previous chapter when we're looking to see if something unusual or not, and we're looking for a particular value. You want to look at that value and either below or above, depending on which kind of tail it's on, because it's sometimes challenging, or not challenging, it's sometimes, what's a good word? Unlikely to get a particular one value by itself, especially when you have many, many, many values in your distribution. So you want to look to that value or lower or higher, depending on which tail it is, because it's going to give you a little bit more of a reasonable guesstimate to see if it's unlikely or likely. So keep that in mind. Okay, here's a visual. This is very important for us to know. On the far left, we have a population distribution. So all the things. I don't know what we're talking about here, but half of, or 100 are red and 100 are blue. So parameter here is 0.5 for red. Excuse me. Then from this population, we take simple random samples. Notice how they're the same size of 20. And we get different distributions each time, which we would expect. Now, if we were to do this many, 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 many times. So in this one, the sample proportion of red was 0.4. In this one, it was 0.55. In this one was 0.65. If we were to then do this many, many times, we would then get our sampling distribution, right? So this sampling distribution is actually not a true sampling distribution because it just comes from 500 samples, so it's an approximate sampling distribution. This describes how a statistic varies in many samples from the population. So here, these columns represent individuals, okay? This here represents the samples, how they varied, okay? So individuals, samples. Another visual to help us out, we take lots of different samples. We take, for instance, their average, and then we make a distribution of those averages. So the sampling distribution is the distribution of a statistic across an infinite number of samples. There are actually 3 distinct distributions involved. I'm saying this a lot because it's important and also a little confusing. The population distribution gives you the values of the variable for all the individuals in the population. The distribution of sample data shows the values for the variable for all the individuals in the sample. Now, this is the one we're talking about in this chapter and focusing on. The sampling distribution shows the statistic values from all possible samples of the same size from the population. There's a difference between the distribution of the sample data and a sampling distribution. This is why how you say it, how you write it, how you speak it is so, so, so important. Okay? Next video is going to carry on more from here.